Hi, I'm Dr. Jason Brinkley, and this is Concentration-Dependent Solution Properties. By the end of this video, you will be able to describe and explain concentration-dependent solution properties and perform calculations involving colligative properties. What are colligative properties? Colligative properties are those properties of a solution that require only the concentration to be known, not the nature of the not the identity of the solute. The only thing we need to know is the concentration of the particles present. Now, the colligative properties we're going to discuss are vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. So let's start with vapor pressure and Raoult's law. A non-volatile solute will decrease the vapor pressure of the solvent in proportion to the solute's concentration. That is what we call Raoult's law. Now, what happens is the addition of a non-volatile solute actually impedes the conversion of the solvent being turned into a gas because of the attractive forces between solvent and solute particles. So you can see here, we've got pure solvent and solvent with a solute. The solute can impede the movement of the solvent into the gas phase. The next thing we're going to talk about is freezing point depression. Now, freezing and melting are in equilibrium at the freezing point or the melting point. It depends on which direction you're going. Are you heating it up? If you're heating it up, that's the melting point. If you're cooling it down, that's the freezing point. Now, this equilibrium exists when the rate at which the melting and the rate at which the freezing of the solvent are equal. So you've got some solvent is melting, some solvent is freezing. The rate at which that happens, if that's equal, that's the freezing point. Okay? Now, what solute particles do is they impede the rate at which the liquid forms the solid, which is the forward reaction here. So we've got water as a liquid going forward to water as a solid. It slows down this forward reaction, where lowering the temperature allows the reverse reaction, the solid to the liquid, to slow, and the solution will freeze. So that is why the presence of a solute decreases the freezing point. Now, because in northern Illinois we have winter, we add salt to our sidewalks to help melt the ice. What does it do? Does it really melt the ice? No, it lowers the freezing point of the water in the ice so that it requires much colder temperatures to freeze than what the ambient temperature is. Boiling point elevation is very similar to freezing point depression in that Raoult's law shows that the vapor pressure is lowered by the presence of the solute because of the attractive forces present in the solute to solvent interaction. Now, what the vapor pressure lowering means that more energy needs to be added to the system to raise the vapor pressure to atmospheric pressure. Remember, that's what we call the normal boiling point. When the vapor pressure equals atmospheric pressure, that's the normal boiling point. So the temperature of boiling needs to be higher. Now, why did I say that it was similar to freezing point depression? Well, it turns out they have the same relationship. Freezing point depression and boiling point elevation, they have the same mathematical relationship. Delta TF is equal to KF times the solute particle concentration, and delta TB, change in temperature of boiling, is equal to KB times the solute particle concentration. So the changes in the boiling or freezing point are proportional to the solute particle concentration. Now, we can't use molarity because molarity is a temperature-dependent concentration unit, okay? Because as we change temperature, the volume of our solution will change. So we need a solution concentration measurement that doesn't change with temperature, and that is what we call molality, little m. Molality is temperature independent, and it is moles of solute per kilogram of solvent. So there's no volume measurement in this that can change. It's a moles to mass relationship. Now, the molality of a solution depends upon whether the solution is an electrolyte or a non-electrolyte. If we have a non-electrolyte, like glucose here, 1 C6H12O6 dissolved in water gives you 1 C6H12O6 aqueous. It's a 1-to-1 relationship. It doesn't break apart into ions. How do I know it doesn't break apart into ions? Remember that molecular compounds generally don't break apart into ions. So this is a non-electrolyte. So 1 mole of glucose gives you 1 mole of particles in solution. Now if you have an electrolyte, like sodium chloride, when I dissolve sodium chloride into water, I get sodium ions and chloride ions. That gives me 2 particles per every 1 mole, two particles for every 1 particle of sodium chloride, or 2 moles of particles for every 1 mole of sodium chloride particles. So 1 mole of sodium chloride gives me 2 moles of particles in solution. Now that's important because if you recall, delta TF and delta TB is proportional to the constant KF, or KB, times the molality of the particle concentration. So if I have a 1 mole solution of glucose, that's different than a 1 mole solution of sodium chloride. A 1 mole solution of sodium chloride is actually 2 mole in ions. Now, water has a KF and a KB shown at the right here. KF is equal to 1.86 degrees C per mole, and KB is equal to 0.512 degrees C per mole. So you can see the equations become delta TF is equal to KF times the molality of particles, and delta TB is equal to KB times the molality of particles. So if we know the nature of the solute, whether it's electrolyte or non-electrolyte, and the molality, we can calculate the change in the freezing point or the boiling point. So let's do one of these calculations. Calculate the boiling temperature and freezing temperature of a solution that's 1.5 mole solution of glucose. Remember that glucose is a covalent, non-dissociating solute. So what we're going to do is we're going to calculate the delta TF and the delta TB. So delta TB is equal to KB times M of the particles. Since this is non-dissociating, the number of particles equals 1. So this becomes delta TB equals KB times M. Or delta TB is equal to 0.512 degrees C per mole times 1.5 mole. Molality cancels, and we're left with degrees C, and that's 0.768 degrees C for the change. Now, this is boiling point elevation. So to get the boiling point, we take 100, the normal boiling point of our solvent, water, and we're going to add 0.768 degrees C to give us 100.77 degrees C for our new boiling point. Okay. Then we're going to do the same thing with our freezing point. Delta TF equals KF times M of the particles. But that becomes simply delta TF equals KF times M, since the number of particles is 1. Or delta TF is equal to 1.86 degrees C per mole times 1.5 molal. Molality cancels, and we're left with 2.79 degrees C. But this is freezing point depression, so we're going to take our normal freezing point of water, 0.00 degrees C, and we're going to subtract 2.79 degrees C, and we're going to get negative 2.79 degrees C. So we can see that the boiling point is much more or much less affected by the presence of the solute than is the freezing point. The freezing point is definitely affected. Let's do another calculation. This time we're going to calculate the temperature of boiling and freezing of a 1.5 molar solution of KCl. Now remember, this is a 1 mole of KCl gives us 2 moles of particles. So that means delta TB is equal to KB times M times 2 for the number of particles. So delta TB equals KB, which is 0.512 degrees C per mole, times 1.5 molal, times 2 now, and that gives us 1.54 degrees C. We add that to our 100 degrees C, and we get 101.54 degrees C. So you can see the number of particles plays a large part in the increase in the boiling or freezing point depression. Let's see how much it changes the freezing point depression. Delta TF equals KF times M times 2, or 1.86 degrees C per mole times 1.5 molal times 2 gives us 5.58 degrees C. 0.00 minus 5.58 degrees C gives us a negative 5.58 degrees C. So you can see adding sodium chloride or potassium chloride or any dissociating solute, any electrolyte solution, is going to double or maybe triple, depending upon the number of particles, the freezing point depression as compared to something that doesn't dissociate, like sugar. We don't put sugar on our sidewalks, although we could. It's just not nearly as effective. Let's now talk about osmosis, osmotic pressure, and osmolarity. Osmosis is the diffusion of water across a semi-permeable membrane in response to a concentration gradient. A concentration gradient is where you have an area of high water concentration to an area of low water concentration, or high solute concentration is an area of low water concentration. Low solute concentration is an area of high water concentration. So what happens if we take a solution and we put it into a dialysis bag? This is our semi-permeable membrane. Semi-permeable means it allows water to pass, but not larger solute particles to pass. If we place a solution with some solute and some water in there into a pure water environment, water is going to flow from an area of high concentration of water to an area of low concentration of water. So there's a higher concentration of water outside the bag than there is on the inside of the bag. And notice the water level, the liquid level in our bag starts to increase. And at some point, we hit a time when the rate at which the water is diffusing from the beaker into the bag and the rate at which the water is diffusing from the bag to the beaker is the same. This is the equilibrium concentration inside the bag and the or not the equilibrium concentration, but the equilibrium that exists between the bag and the beaker. Okay? When that equilibrium happens, what we have is a pressure. And this is the pressure required to stop the movement of osmosis across a membrane. As we saw in the previous picture, that happened when the height of the column of water inside the bag got to a certain height. That pressure that was pushing down from the column of water equaled the osmotic pressure. Okay? Now, in order to understand osmotic pressure, we need to understand something called osmolarity. Now, osmolarity is very similar to the molality that we just went through, in that it is the concentration, this time in molarity, times the number of particles of solute. Okay? Number of particles per mole of solute. In other words, glucose gives us 1 mole of particles for every 1 mole of glucose. Or KCl gives us 2 moles of particles for every 1 mole of KCl. So that's what I is. I tells us the number of particles per mole of solute. And osmotic pressure looks a little like the ideal gas law, in that it is pressure, pi, osmotic pressure pi, is equal to I times M times RT, where M is moles per liter, I is the number of particles per mole, R is the ideal gas constant in units of liters, atmospheres per mole Kelvin. So that, as a reminder, is 0.0821 liter atmospheres per mole Kelvin. And T is temperature in units of Kelvin. So pi equals IMRT. Pi IMRT. So let's do an osmolarity calculation first. Determine the osmolarity of the following solutions. We've got a 5.0 times 10 to the minus 3 molar ammonium nitrate, which is, they're telling us, is an electrolyte, and 5.0 times 10 to the minus 3 molar glucose, which they're telling us is a non-electrolyte. So let's do part A. 5.0 times 10 to the minus 3 moles per liter of ammonium nitrate. Remember, that's what molarity means. Times, now, since this is an electrolyte, it breaks apart into 2 ions, the ammonium ion and the nitrate ion. So 2 ions for every 1 mole of ammonium nitrate gives us 1.0 times 10 to the minus 2 molar ion concentration, or osmolarity. Part B, we've got the 5.0 times 10 to the minus 3 moles of glucose, which I'm going to just abbreviate as gluc per liter, times now 1 glucose for every 1 mole of glucose, equals 5.0 times 10 to the minus 3 moles or molar glucose concentration, or its osmolarity. So osmolarity is simply the molarity times the number of particles it dissociates into, if it does dissociate. Let's do an osmotic pressure calculation. So the osmotic pressure of a 0.5 molar potassium nitrate solution. Remember, pi equals IMRT. Potassium nitrate is an electrolyte, so this dissolves and gives us 2 ions per mole. So I equals 2. M is equal to 0.50 molar. R is equal to 0.0821 liter atmospheres per mole per Kelvin. And temperature they don't give us, so we're going to assume 298 Kelvin, which is 25 degrees C. So let's calculate the osmotic pressure. Pi equals 2 times 0.50 molar, or moles per liter, times 0.0821 liter atmospheres per mole Kelvin, times 298 Kelvin. Kelvins cancel, moles cancel, liters cancel. We're left with units of atmospheres, and we get pi equals 24 atmospheres. So it requires 24 atmospheres of pressure to stop osmosis in a 0.5 molar potassium nitrate solution. Now, along with osmolarity comes the biological aspect, what we call the tonicity of a solution. Tonicity is a measure of effective osmotic pressure in a solution. We have 3 different types: hypo, hyper, and iso. A hypotonic solution is a solution with less osmolarity as another solution. In other words, less concentration. So a 0.1 molar sodium chloride versus 1 molar sodium chloride. 0.1 molar sodium chloride is hypotonic compared to the 1 molar sodium chloride. Hypertonic is a solution with a greater osmolarity as that of another solution, or a higher concentration. In other words, 1 molar sodium chloride versus 0.1 molar sodium chloride. This is hypertonic compared to the 1.1 molar sodium chloride. And isotonic means a solution with the same osmolarity as another solution. In other words, a 1 molar sodium chloride, which is an electrolyte, versus a 2 molar glucose, which is a non-electrolyte. Remember, the osmolarity of this is 1 molar times 2, or 2 osmolar sodium chloride. This is 2 osmolar glucose. 2 molar times 1 equals 2 molar osmolar glucose. They have the same osmolarity. Even though one is an electrolyte and one is a non-electrolyte, they have the same osmolarity. Now, why is this important? As I said, there's a biological aspect to this. The osmolarity of a solution has to be of a certain range in order to be biologically compatible. So, for example, if I had an IV, here's an IV, a 0.15 mole mass to volume potassium chloride and a 5% mass to volume glucose solution are osmolar to each other. Or are isotonic to each other, not osmolar. They're isotonic to each other, meaning they have the same osmolarity. Now, what happens if we put that IV solution into the body and it doesn't have the same osmolarity as, say, blood? You get, if your solution is hypertonic compared to blood, you get what is known as crenation, or a shriveling of the blood cells. If it is isotonic, so this is for hypertonic, if it's isotonic, you get normal red blood cells. Everything's cool. If it's hypotonic, you get cytolysis. Or the blood will swell up and burst. You can see how this blood cell doesn't have the typical red, dark red dimple here because it's swollen with fluid. Okay? This is also one of the ways that you can perk up celery. Oddly enough, if you have celery that's gone limp in the refrigerator, if you put it into a water solution, the water is isotonic compared to the interior of the cells of the celery, so water will flow into the celery cells and actually fill up the central vacuoles of the cells, which causes pressure to build, what's known as turgor pressure, and the celery will perk up and be crisp as ever. And it has to do with the osmolarity, one being an isotonic, one being a hypertonic solution, and the direction of flow of water from areas of high water concentration to area of low water concentration. So I hope you enjoyed this video, and I look forward to seeing you in the next.